Hello everyone, welcome to our lesson on proving Markov's inequality. In a prior lesson, we have given an intuitive explanation of Markov's inequality. And since I've promised you that I will have a follow-up lesson proving Markov's inequality, this lesson is just dedicated to proving Markov's inequality. In the prior lesson, we have looked at if we have a random variable x that takes non-negative values, that's important, and for which we have a good estimate of the expected value, or the average. We know the average, or we can estimate it. And thirdly, this random variable is not degenerate at zero. That is, not all the point masses degenerate at zero. Then we can say something about the probability of x exceeding some constant k greater than zero. And that probability is less than or equal to, or is at most, the expected value of x divided by k. For intuitive explanation, I recommend you go back and watch our video on introduction of Markov's inequality. I'll put the link in the notes of this video. Now I want to prove that inequality here. So I'm going to actually start with the right-hand side and then show that this inequality is true. So I want to prove, one way to prove that is the expected value of x divided by k is greater than or equal to the probability that x value is greater than or equal to k. Let's start with a discrete random variable case where we have a discrete random variable which takes values of either 0, 1, 2, 3, and so on, non-negative integers. What is the expected value of a random variable that takes those non-negative integers? The expected value of x in those cases is equal to the sum of x times the probability that random variable takes a value equal to little x. Okay? Now, maybe it's simpler to just have a toy example on the side so that it helps with understanding of how we proceed in the proving of this theorem. Let's say we have a probability mass at 0, a probability mass at 1, at 2, at 3, at 4, and so on. To make things again even simpler, let's take the constant k is equal to 2. If I write down this summation of the expected value of x, then I have 0 times the probability that x equals 0, plus 1 times the probability of x taking 1, plus 2 times the probability x taking 2, plus 3 times the probability x taking 3, and so on. What I want to do is, what happens if I exclude from the summation the first k minus 1 terms? So if I don't include them in the summation, then essentially for this example, I'm excluding 0 times p equals 0 and 1 times the probability of x equals 1. Then I am reducing the overall value of the summation, or the overall value of the expected value. So therefore I can say the expected value of x is greater than or equal to 2 times the probability of 2, plus 3 times the probability of 3, plus 4 times the probability of 4, plus ... I can only say that because x is non-negative. If x were to take negative values somewhere in this summation, then it is not true that the expected value of x is greater than or equal to 2 times probability of 2 plus 3 times the probability of 3, and so on. Okay, that's an important distinction. And the summation here, one way to write this would be this expected value is greater than or equal to the sum as x goes from k to infinity. So I'm excluding the first k minus 1 terms. I want to do something else next. What happens if I replace x inside this summation by the constant k? Okay, so instead of k times the probability of x equals k plus 1 times the probability of x equals k plus 1, plus k plus 2 times the probability of x equals k plus 2. If I just used a constant multiplier of those probabilities instead, then I would have k times the probability of k plus k times the probability of k plus 1, plus k times again the probability of k plus 2. Then again, I am making the overall expression smaller. In this concrete example, 3 times the probability of 3 is greater than 2 times the probability of 3. All right? And 4 times the probability of 4 is greater than 2 times the probability of 4. If I'm making the overall expression smaller, then I can say this summation here is again greater than or equal to the summation of x equals k to infinity of k times the probability of x. Essentially, on the right hand side, from the small example that I have here, you can take out 2 or k as a common multiplier, and therefore you can write this expression as 2 times the sum x equals 2 to infinity of the probability of x. Or in general, I can write this as k times the sum x equals k to infinity of the probability of x. And now, if I go back to this discrete case again, if I was just summing the probabilities of x greater than or equal to 2, then what I have here is 2 times the probability that x is greater than or equal to 2. If I apply the same logic here, then I have this expression here, the summation, times k is equal to k times the probability that x is greater than or equal to k. Expected value of x greater than or equal to k times the probability that x takes values of k or more. If I rewrite this, I get what I have up here as Markov's inequality. A similar approach also works for a continuous case. So let's go through that quickly. Let's say we have a continuous random variable y that has a probability density function given by fy, and y is non-negative. That is, it takes the set of real numbers greater than or equal to 0. And Markov's inequality, to just write it again, is the probability that y is greater than or equal to k, a constant k greater than 0, is bounded by or is at most equal to the expected value of y divided by the constant k. To prove this, I'm going to start with the right-hand side. I'm going to show the right-hand side is greater than or equal to the left-hand side. The right-hand side has the expectation in the numerator. So the expected value of y for a continuous random variable is the integral, and this is a non-negative continuous random variable. So the integral from 0 to infinity of y times f of y dy. And I'm just going to plot a probability density function of a non-negative random variable y, just to make sure we have a visual representation as we go through the proof. This integral is equal to the integral from 0 to the constant k. All right, I'm going to write the constant k here on the plot. The integral from 0 to the constant k of y times f of y dy, plus the second component that I have left out in the first expression, that is the integral from constant k to infinity of y times f of y dy. So we've got two integrals summed up that give us the expected value. If I ignore the first integral here, since y is non-negative, that is, it takes values of 0 or above 0, ignoring that component, the expected value is greater than or equal to this second integral here. Now, I'm going to do a similar thing that I did for the discrete. I'm going to replace this y in the integrand that multiplies the probability density function by the constant k. So, what do you expect the relationship between this integral, the integral from k to infinity of y times f of y dy, and the integral from k to infinity of k times f of y dy? This, for example, let's take k, let's say k is 100, all right? And in the integral, when k, for example, when k equals 200, the integrand would have been 200 times f of 200 times dy, but rather it's going to stay as 100 times f of 100. For y greater than k, for the values of y greater than k, k times f of y is actually less than y times f of y. So the expected value of y is, again, greater than or equal to the integral from k to infinity of k times f of y dy. And I can take k outside of the integral here, and that gives me k times the integral k to infinity of f of y dy. And this integral is actually equal to the probability that y is greater than or equal to k. So, putting things together, now we have the expected value of y for a continuous random variable y greater than or equal to k times the probability that y is greater than or equal to k. Rewriting this, we get the Markov's inequality, which is the probability that y is greater than or equal to k is less than or equal to the expected value of y divided by k for a constant k, and for a random variable y that is a non-negative and is not degenerate at 0. All right, thank you. And if you like this video, please subscribe, and also feel free to share this video with your friends. And thanks for watching.